This video is going to be pretty short, and there's no real MATLAB work to do. This is kind of combining everything we know from the first 3.5 chapters. And the title is the invertible matrix theorem. So the key here is the invertible matrix theorem, and we have the following are all equivalent. We looked at these both in the one-to-one and onto transformation section, but now we're going to talk about having a matrix A that is a square matrix. It's n by n. And we're also going to talk about what happens to the transformation associated with that matrix. And we have the following statements are all equivalent. And one is, well, suppose that A is an invertible matrix. All right, well, if A is an invertible matrix, the following are all equivalent. In other words, I can use 2 through 6 as ways to find out if A is invertible, or if A is invertible, I know that items 2 through 6 are true. So if A is invertible, then A has n pivots. So one way to tell if A is invertible is to check how many pivots it has. And if it has a pivot in all of its columns and all of its rows, then it is in fact invertible. I know that if A is invertible, then the null space of A is only the zero vector. There's only one vector in the null space. So remember, the null space is all possible solutions to the homogeneous equations, which is A times the vector x is equal to the zero vector. And if the zero vector is the only thing in the null space, right, if the only thing that x can be to make this system of equations true is the zero vector, then I know that A is invertible, that the matrix A is invertible. If A is invertible, then the columns of A are all linearly independent. So once again, if I happen to know that all of the columns of A are linearly independent, then I know that A is invertible. If I take, for example, a linearly independent set of vectors and combine them into a square matrix, then if I combine them into a matrix and it turns out to be square, then I know that that square matrix is invertible. I also know that the columns of A span Rn, which is the same thing as the associated matrix transformation being onto. I know that the matrix equations, A times the vector x equals the vector b, has a unique solution for each vector b in Rn. That's the same as it being one-to-one, right? Because not only does it have a solution, so having a solution means that it is not inconsistent when I row reduce it, but saying that it has a unique solution is saying that it is the same as one-to-one. Also, T is invertible. So in calculus, I know that a function f that is continuous and is one-to-one and onto, then that function has an inverse, right? Well, so now we're looking at the function, the linear transformation t, which is a function, and we're going to say, hey, how do I know when t is invertible? Well, like we said, 5 implies 9, right? So if the columns of A span all of Rn, then t is onto, and if we have a unique solution for each b in Rn, then t is one-to-one. So just saying that t is invertible means that this function t, the transformation, is invertible. So that's what the invertible matrix theorem says. There'll be some additional points. These are not the only 9 things that are true about about an invertible matrix, but it's the key ones. And again, the way we're usually going to check to see if a matrix is invertible, or one key way we're going to check is to take it in RREF form and check how many pivots it has. But every single one of these things will be true. So going forward, this is going to be a really useful checklist, and we'll add to this checklist of things that are true when the matrix A is invertible.